Now we're going to look at how to use Gauss's law to work out the electric field from various charged shapes. The first shape we're going to look at is a charged solid sphere with a charge density of ρ. We can work out the total charge from the sphere, which is just the volume times the charge density. First of all, we're going to look at drawing our Gaussian surface outside of the sphere, which means all of the sphere is contained within the surface. Starting with the left-hand side of Gauss's law, we write down the law, which looks like this. E is the electric field due to the charged sphere, and dA is a vector of length 1, normal to the surface, and of the size of a tiny chunk of the surface area of the sphere. E is parallel to dA at all points on the surface, so the dot product just results in the magnitudes, so we can remove the dot and the underlining. E is a constant at all points on the surface, so it can be taken out of the integration as we've done here. Integrating over the whole surface gives us this. If we now equate to the right-hand side of Gauss's law, which is another expression for the net flux through the Gaussian surface, we can rearrange to find an expression for the electric field. So that's the electric field due to this charged sphere. With the Gaussian surface outside the sphere, we can see that the total charge from the sphere is always enclosed by the Gaussian surface, however large we draw it, i.e. it doesn't depend on r. The next case we're going to look at is drawing the Gaussian surface inside the solid sphere, so that only part of the charged sphere is inside the surface. Working through Gauss's law, we end up with the same left-hand side. When we integrate over the surface, we still get 4 pi r squared, even though the r is smaller in this case. But then, when writing the right-hand side of Gauss's law, we can't just write the whole charge is enclosed anymore. We have to write the charge enclosed as the charge density times the volume. In this case, as the charge density is the same everywhere, it can be brought out of the integral, and then integrating the volume up to the Gaussian surface gives 4/3 pi r cubed. Rearranging to find E then gives us this, for the case when the Gaussian surface radius is smaller than the radius of the solid sphere. The charge in this case does change with r. The next shape we will look at is a charged hollow sphere, or a shell. Firstly, let's put the Gaussian surface outside of the charged shell. When we use Gauss's law and integrate over the surface, we get exactly the same for the left-hand side of Gauss's law as with the charged solid sphere, and we also get exactly the same right-hand side, as again the total charge of the shell is fully enclosed by the Gaussian surface. So as both sides are the same, we end up with the same result for the electric field. So the electric field for a shell and for a charged solid sphere with a Gaussian surface outside of them is exactly the same. If we draw the Gaussian surface inside the hollow sphere, then the total charge contained is 0. So the right-hand side of Gauss's law will be 0, and then rearranging for E gives us the electric field equal to 0. So this means that the electric field inside the charged shell is 0. Remember when we talked about forces inside charged shells before, you can kind of think of it as the charges on the shell cancelling out on the inside, which happens at all points inside, not just in the centre. So for example, if you have a balloon, which is essentially a hollow sphere, and it has built up some static charge, then whilst on the outside you experience an electric field from it, there is none at all on the inside.